Hi everyone, in this video we're going to be talking about buffers and titrations. So first let's break it down. What on earth is a buffer? So a buffer is anything that resists changes in pH. So a kind of really good example of a buffer that I actually discuss in another video on this channel is the bicarbonate buffer system, which our own human body runs. And this is to resist changes in pH. So our body likes to be around a particular pH range. And if it's getting disrupted from that pH, that can cause a lot of problems. For us, and it can even lead to death even. So it's really important that we have that buffer system in place so that we can resist those changes in pH. So yeah, that's basically what a buffer is. And what is a titration? So a titration is basically something that we're doing in order to find the concentration of an unknown compound. Or, an unknown substance. So there are some things that we have to understand about buffers before we get into this. So a buffer, we know, resists changes in pH. But a buffer usually consists of a weak acid and its conjugate base. So it's consisting of a weak acid and its conjugate base. So how do we know so we know we have a weak acid. So we know we're working specifically with pKa. So how do we know what pKa that we want? So the way this is done is that we want to have a pKa that is close to the pH at equivalence point. So at the equivalence point of the titration, which we're trying to find the concentration of some unknown thing, we want our weak acid of the buffer, we want its pKa to be as close as possible to the pH of the acid at equivalence point. So now let's run a titration. So a titration is, we have this flask here, and we have this large burette. And this burette is going to have something called the titrant. This is the known substance that we are adding to our unknown. And our unknown is called the analyte. So we're going to keep adding this here until we see something that helps us know that our titration is done, and now we can try to figure out, pH, concentration, things of that sort. So say we have an unknown analyte and it's a base, or let's say it's an acid. And our titrant is a base, and we are adding this base into this acid. Right? So how do we know, how do we know when we're done? We know when we finally get our indicator that we added enough base that this acid is completely deprotonated. Because the whole purpose of a base is to deprotonate an acid, right? If you need a refresher, I did make a video on acid-base chemistry that you can take a look at. So there are different types of titration curves that come about. So one is if we have a weak acid with a strong base. So on our y-axis, we have pH. And on our x-axis, we have volume added of the titrant to the analyte. So now if we have a weak acid, so let's just say we have 1, 2, 3, 4, 7, and then we have 14 here. So if we have a weak acid, we know that an acid's pH is less than 7. But since we have specifically a weak acid, we're going to have something a little closer to 7 than it is to 1. Because if it's closer to 1, that means it's a very strong acid. But we have a weak acid in the situation. Let me actually give us more space here. All right, so we have a weak acid. So, we're going to be starting at about here. we're not too close to, this really strong acid area. So over at pH, we're starting about here. And a titration curve will always look like this. It'll look like an S. Okay, so now what are the parts of this S that we need to know? Well, first of all, we know that we're starting off a little closer to 7 because we have a weak acid. And in the end, we're ending up over here really close to 14 because we have a strong base. So we're ending up really close to 14. So there are parts of these curves that we need to understand. First of that is this. So this is kind of like our symmetrical point of this little curve, and this is called the equivalence point. So the equivalence point is basically when we have our weak acid, right? Our weak acid, it has been completely deprotonated by the strong base. So say our weak acid was HF or something, and let's say our strong base was NaOH. In this situation, we know that that hydrogen there, that's gone. We're just left with the conjugate base, which is an F- ion, a fluorine ion. And that's what's happening at the equivalence point. We have completely deprotonated our acid. And then there's another important point to know, which is about here. And this is called the half equivalence point. And you can see I found where our equivalence point is, and I cut it in half, right? And that's how we have our half equivalence point. The half equivalence point is exactly what it sounds like. It is halfway to the equivalence point, so we haven't deprotonated our acid yet, but we do have the same amount of acid as we have base. So the concentrations of the acid to base are 1-to-1. So one way I think we can understand this is by using the Henderson-Hasselbalch equation. So if you don't remember the Henderson-Hasselbalch equation, is this. So this basically helps us find the pH at different points of our titration curve. So what did I say? I said at the half equivalence point, we haven't completely deprotonated. So we have an equal amount of acid and base. We have a 1-to-1 ratio. So an acid and its conjugate base are 1-to-1. So what does that mean? We are going to have 1-to-1, so let's fill that in. pH equals pKa plus log of 1/1, which is just 1. And then the log of 1 would be 10 to the what equals 1. 10 to the 0 equals 1. So the log of 1 equals 0. So we can cancel that. We have pH equals pKa. So this is a really important property that you have to understand. At the half equivalence point, the pH is equal to the pKa. And this is true of any monoprotic titrations. So let's look at another titration. Let's say we have a strong acid, but a weak base is added to it. So now we are starting off strong. We're a strong acid, so we're going to be closer to 1. And we're ending a little closer to 7 for the base because we have a weak base. So we have strong acid, weak base. Our equivalence point is less than 7, so we have an acidic equivalence point, which makes sense because we have a stronger acid than the base. And again, we have our half equivalence point where we just reviewed the pH is equal to the pKa. So we can have multiple different combinations. So when we could also have a weak acid and a weak base. We could also have a strong acid and a strong base. I recommend that you try these two out on your own, because using the same tips and tricks that we observed over here, just basic observations about what makes a strong acid strong, what makes a weak base weak, and what makes a strong base strong, any combination. We know that a strong acid has a pH closer to the 1 and it has a higher pKa, and a strong base has a pH closer to the 14. So you can try to use that, figure out where your equivalence point will lie, what our initial and final pH asymptotes will be. So I recommend you try to do these two on your own. And that's about it. That's basically what you need to know about buffers and titrations at a very surface level.